is Prof. Thomas Kiel, who will be talking about multi-scale modeling of chemical systems on HPC and quantum computers.
So hi everyone, thank you very much for the introduction, and thanks very much to the organizers to let me speak at this wonderful event. It's really great to be here. So my talk is going to be about challenges in chemical simulations. And because it's an HPC conference, I'm going to try and focus. I'm going to give you a flavor of some of the scientific challenges that we look at, but I want to focus really on the computational challenges, and that's in two different respects. One in terms of how do we scale up chemical simulations to the latest and largest supercomputers in the exascale era. And then the second one is how do we make use of emerging computational technologies, in particular quantum computing, to do kind of real-life chemical problems and not just proof-of-concept calculations. But just before I get onto that, just to say a little bit about where I'm coming from. So I work for the Science and Technology Facilities Council in the UK. This is one of the funding research councils that gives out money for research, and it also looks after the UK's national laboratories at Daresbury, where I'm based. That's near Manchester and Liverpool, and also Harwell near Oxford. Thanks. And I'm part of the scientific computing department at STFC. So we're based at both these sites, and our remit is to create tools, so computational software, to help academic communities and industry to perform modeling work and other computational work across the whole range of science domains. And we also support the UK's large experimental facilities like the Diamond Light Source, ISIS neutron source, and the UK Central Laser Facility. And we take a collaborative approach to doing research and development, so working with groups in academia and industry to pursue scientific challenges that our computational codes enable. So I lead the Multiscale chemistry group in the scientific computing department. And I should kind of explain what we mean by multiscale, because even in our department, people use multiscale to mean different things. So the engineers have their own conception of multiscale, which is completely different to ours. So what we mean by multiscale is what's called QMMM methods, which combine the electronic scale, so electronic structure calculations, with the atomistic scale, where we forget about electrons and just model atoms, which allows us to reach larger length and time scales. And the reason we do these simulations is to avoid some of the computational cost of doing expensive chemical calculations. So we could, in principle, do a quantum mechanical simulation of an entire complex chemical system. But if you have any familiarity at all with computational chemistry, you'll know that these become very expensive very quickly. So QMMM methods are a way to avoid those limitations. And in the QMMM approach, what we do is we identify a part of our system which is important to describe electronically. So it might be, for example, where a chemical reaction takes place in a protein. It might be a molecule absorbing onto a solid state surface. Wherever electrons are important, that's what we use our QM calculations. But then for the chemical environment around that, we might not need such a complicated description. We can use a classical force field to represent that part, and we can still get accurate results. And that massively reduces the computational cost of the calculation, but it keeps the accuracy where we need it. So that's our focus. We develop a code at Daresbury called ChemShell. So this is a general purpose computational chemistry environment that's scriptable in Python, but it has a particular strength for doing these multiscale QMMM calculations, and I'll tell you a bit more about that in a minute. It's widely used for biomolecular modeling and also materials chemistry, which is what I'm going to be speaking about in the first part before moving on to the bio side. I don't really have time to go into a proper overview of the ChemShell code, but if you want to know more, we've got a review that came out last year in PCCP, so do take a look at that, and that covers all the latest developments in the code. Visit our website and go to your social media of choice, and you can find out more there. So one thing that's important to note about ChemShell, and this will be very relevant to the HPC and quantum computing aspects that I talk about later, is the way that it's designed, and that is in a very modular way. So ChemShell itself doesn't do QM calculations or MM calculations itself. It calls out to external codes. So let's say your favorite quantum mechanical code is NWChem, your favorite MM code is Gulp. ChemShell will call out to those codes that you choose to do those parts of the calculation. And then ChemShell will take care of all the fiddly bookkeeping that combines the two together. So there's a lot of kind of accounting for what's happening at the boundary between the two parts of the calculation, and ChemShell handles all of that for you. But it also does higher level chemical tasks as well. So it has modules for doing geometry optimizations, molecular dynamics, spectroscopic signatures, and so on, all the kind of things that you might want to do with a chemical software package. And just to give a very brief flavor of the kind of calculations that we do in ChemShell, so this is a collaboration with our colleagues at UCL, so Alexei, who's here with us as part of the same team, and Richard Catlow's group. So this was work carried out by Jamal Nazir, who's in Richard's group, and he wanted to look at a very important pollution problem, which is the emissions of nitrogen oxide, NO and NO2, from combustion, so things like industrial combustion, but also engines in vehicles. And in the UK and other countries, it's actually mandated that these nitrogen oxides are reduced by a catalytic process called SCR, which uses ammonia. And zeolites are a good performing catalyst for doing this reaction. And that's the reaction that's shown there on the right-hand side. But as is often the case with industrial catalysts, not everything that's known about this reaction is not completely known. And in particular, the effects of solvents, so H2O and ammonia, is not fully clear, and there appears to be some kind of competing effects. But it wasn't clear how, from experiment, what these effects were. So Jamal set off to do some simulations on this code on the system using ChemShell. It did a kind of standard QMM treatment. So this is a cluster of zeolite on the left with a QM region where there's a copper species, which is where the catalytic activity takes place, with 100 or so QM atoms around it. So that is our expensive QM part of the calculation, and the rest of the zeolite you see is treated by the more cheap MM method. And what Jamal found was that actually there's quite some very interesting and nuanced solvent effects that go on in this system. So in the oxidative part of the reaction, of the catalytic cycle, that's where copper plus goes to copper 2 plus. The effect of the solvent is actually to reduce the energy of the different species, the different intermediates in the catalytic cycle. And this means that it's promoting that part of the catalytic cycle. And that's the case for both ammonia and water. On the other hand, when we have the reductive part of the catalytic cycles, that's when Cu2 plus is going to back to Cu plus, completing the cycle. The effect of the solvents, this is the green and the red parts in that energy diagram, is actually to raise the energy, and so it inhibits the process. And so from the point of view of doing simulation, we can see now why it is that there's unclear solvent effects from experiment is because there's actually two very clear competing effects at the different parts of the catalytic cycle. So that's an example of the kind of science that we can do with QMMM. And now I want to move on to HPC aspects. So how do we get these multiscale simulations to work at very, very large scale, so exascale type problems? And this work is part of the UK's Excalibur program. So this was a £50 million investment over the last 5 years into UK simulation codes and trying to make them ready for the exascale era, so making them usable on exascale platforms around the world, and also hopefully in the future in an exascale computer that comes to the UK. And I'm part of a project called PAX HPC, so this is one of the largest projects that comes under the Excalibur banner, that's led by Scott Woodley at UCL, who's also here, And we have a number of people from the PAX team at this conference. So you may have met them if you came to our materials modeling workshop on the Sunday. If not, please do come and say hello while we're here. So this work that I'm about to talk about is by Rajani in my group. There's also Marcello from STFC who'll be talking tomorrow, as will Matt Smith from York, and Scott talked yesterday. So PAX, I'll just explain what PAX HPC is all about. So this is, PAX HPC is about particle simulation in general. So it's not just about chemical simulation or materials modeling, but it's about covering all the time and length scales. So right down from quantum mechanical calculations that I've already showed you, up through engineering challenges, so fluid modeling, at a kind of human scales, and then going right up to cosmological scales. So think about modeling galaxies or even entire universes. So really anywhere where you have a simulation method which involves a particle description, the idea is that PAX covers it. And we're trying to find what are the shared challenges across all these science domains. So if you have a particle description in a simulation, actually there's going to be a lot of things that we have in common, even between a galaxy model and a model of an atom. So this is looking at shared computational challenges of these. And broadly, we can categorize the different types of calculations that we do in this area into 3 types. The first is high throughput calculations. This is very large numbers of very small calculations. So an example of this would be something like a global optimization method to run through a huge number of materials and find the lowest energy one. The next one is so-called hero calculations. So this is really what you might first think of about HPC, so doing extremely large-scale calculations on a single system. And then the third type is the type that we do, which is somewhere in between, and it's to do multiscale or even multiphysics calculations where we're coupling different methods together. And this is the one that Rajani is focusing in our part of PAX. And the sort of work that we're doing under PAX is things like looking at how to make all these codes more accessible and more easy to couple together. So putting Python front ends of them, defining APIs that allows them to be connected together more easily. Looking at new parallelization strategies, so especially task parallelization, but also looking at different domain decompositions, or sort of classic HPC techniques. And then there's a particular focus on GPUs, because obviously as we reach the exascale, the importance of heterogeneous platforms becomes ever greater, and we have a number of codes that we're looking into how to get them ready to run on heterogeneous platforms. But our part and the work that Rajani is doing is looking at what we need to do about the multiscale methods that I've talked about already. So this is both the cluster model that I showed you in that NOx case study, but also periodic QMM embedding. So this is particularly important for things like metals, where we need a completely delocalized description of the electrons. And this is very relevant to PAX because it uses a number of the other codes that are of interest and the groups that are involved in PAX, so things like CP2K, CASTEP, Crystal, and so on. So the work that we've been doing in that space is to make use of the API work that's going on in other parts of the project. So for example, the York team have developed an API to the CASTEP QM code. And this takes a lot of work behind the scenes. So the actual end result looks quite simple, but actually the engineering underneath the code is actually the more important bit to make it runnable as a library and then connectable to other codes. And that wasn't possible before. So that has made our life so much more easy because we don't have to do that ourselves, and we can just connect via the API. And that's a good example of how the different parts of PAX are working together. The other thing that we've been doing is enhancing the existing interfaces that we have. So we had an existing interface to CP2K, but we're now looking at how do we run that, making use of GPU resources. So we make sure ChemShell doesn't run on the GPU itself, but it makes sure that it manages the resources in the right way so that CP2K, for example, is running on GPUs, whereas a code that can't run on GPUs, but we also want to run, is running in the right place as well. So we're testing that now on cloud systems, on our own HPC, and then extending that out to other codes as well. And as part of that, we created a set of training materials for this method, and that was what we were demonstrating at the workshop on Sunday. So that was our first rollout of this work. On the other side, we have the more traditional cluster model that was still the best model for using in a wide variety of situations. And here we're looking at how do we make the embedding schemes more flexible, making use of additional computational resources. And one of the things that we're targeting is increasing the number of QM regions. So in the basic QMM model, we just have one active region. But in fact, there's plenty of situations where you may want more than one. So for example, if you have multiple catalytic sites, or you want to look at several defects in one material, then you might want to have several independent QM regions, and that's what we're implementing now as part of that model. So that's the work that we're doing in the PAX project, and in the last 5 minutes, I just want to talk about another project that we're looking into. So that's getting ready for exascale, but we also need to take account of the emerging computational platforms that are beginning to become available. Okay, they're still in their infancy, but we want to be ready for when quantum computing sort of hits the mainstream. And so we have another project which is looking into the challenges of doing multiscale modeling using quantum computers. This is called the Q-Pharma project. So this is an industrial-led Innovate UK project, which is led by an American company called Seek, and they are trying to build a real quantum computing device. But our part of the project is on the software side, so we're looking at how to make use of this device once it's ready to be used, and that's working together with our colleagues in the Hartree Centre, STFC, and the UK's National Quantum Computing Centre, and Riverlane, who are a quantum computing software company. And this is targeting pharmaceutical applications, so it's like, how can we make use of quantum computers in the drug design field? And if you think about what quantum computers are capable of now, okay, we've reached some very significant milestones, so we can do real quantum chemistry on quantum computers. This paper that was a few years old now was one of the first to show that this was really possible on real devices. It's looking at a 4-atom system, so N2H2, and looking at the barrier to it changing configuration from what's called the cis form to the trans form. So this is showing a real reaction path. Obviously, that's all very well, and it's a really significant achievement, but the question for us who are interested in more complex chemical systems is there actually anything useful that we can do with quantum computers as they are now? So one thing that we could do is wait 10, 20, however many years you think it's going to be before a quantum computer is capable of modeling the enzyme on the right, which it definitely can't do now. But the more interesting question for now is there anything useful that we can do with quantum computers as they are at the moment? Unfortunately, we have a good way of doing this, and that is to use the type of embedding methods that we've been talking about in the previous sections. So the work that we've been doing is looking at introducing an extra layer into these QMM models, which is treated on a quantum computer, whether that's a simulated device running on traditional HPC or the real quantum device. From our perspective, it doesn't actually matter where it's running, because we just want the results from the end of the calculation. And you can imagine a small molecule in the center of this embedded calculation that's treated by a quantum computer. Around that, we have a traditional quantum mechanical calculation. We have to be quite careful here because we have too many quantums in this description. So you have to remember whether we're talking about quantum computers or quantum chemistry, both of which have the same acronym, so we're in complete trouble. But hopefully the diagram at least makes it somewhat clear. And then in the third layer around those two, we have our classical environment, just as we've always had when we do multiscale modeling. And the idea is that our code ChemShell, we add extra functionality to it, so it prepares the first part, the quantum computer calculation, and then it also does the QMMM, and it does what it always does, which is combine all the three together. And that's what our part of the Q-Pharma project is all about. Because it's a bit more complicated than that behind the scenes. The workflow for performing the quantum computing calculation, even on a simulator, is actually quite complex. So we actually call out to a QM code, in this case Orca, to generate the integrals that are needed as a starting point for our calculation. This then is fed into Riverlane software called Discover Light, and that writes the quantum circuit. in a particular file format, which is then given to our simulating program called Quest. This is running at the moment just on traditional HPC. It does the quantum circuit simulation. We measure the qubits, out comes the energy, and that goes back to ChemShell. Unfortunately, as is the way with the ChemShell philosophy, the user doesn't really need to know what's going on here, so long as all the different packages are working together. All you need to do is supply your molecule, choose your options, and back comes the energy, in just the same way as you do with a regular QMM calculation. Then we have a embedding scheme that we use for this, just to keep things very simple. It's what's called a subtractive embedding scheme, so it doesn't require too much connectivity between the two layers, or the three layers. It reduces a lot of the complexity of the implementation. So when we introduce that into the workflow, then we have the quantum computing on the right, we have our subtractive embedding driver in a module in ChemShell, and we have lots of Orca calculations going along to fill in all the different parts of that. So we did a proof of concept calculation to check that this was all working. So this is on a very small system, lithium hydride. The LIH is in the quantum computing layer. So this is running on Scaffold Pike, which is a cluster at SDFC. It was running on, each shot for the simulation was running on one node, which had one GPU attached using Quest. And the circuit simulation clearly dominates the part of the calculation. So even for this very small system, if you're running a simulated quantum circuit, it's never going to be competitive with a traditional QMM calculation. But of course, that's what you'd expect. It's only when you actually go to a real device, as we hopefully will do by the end of the project, that it becomes a competitive solution. And we're just looking at benchmarks. So these is benchmarks for the simulated systems. And you can see that, as you might expect, it goes rapidly more expensive as you go to more complicated molecules. And really, methane is probably about the limit of the types of calculations that we can do, because this is for a single shot, and you have to parallelize over many shots to get your calculation out. So in the last stages of the project, we'll be looking to do embedding calculations using systems of this size. And then hopefully at the end of it, when the hardware is ready, running them again on the final hardware. So just to wind up, so the current limitations are everything's running in a simulator, but there is a device on the way that we're going to be using. And also there's some aspects of the embedding schemes that are limited. So we're limited to a specific type of embedding, and also doing gradients numerically. But these are all things that are relatively straightforward programming challenges. So that will be something that we'll look at as follow-up work. Okay, and that's everything I wanted to say. So just thank, in particular, Jamal for the NOx case study, Rajani, who did the PAX HPC work, and Joe Thacker in my group, who was doing the Q-Pharma project, and all our collaborators at UCL and other institutions. And thank you very much for your time.